In the previous modules, we have discussed the different types of clustering methods. Broadly, these are of two types, the hierarchical clustering methods and the partitioning methods. We have discussed the hierarchical clustering methods in details, both the agglomerative type and the divisive type. In today's lecture, we would be talking about the partitioning method. Now remember that the hierarchical clustering methods are done when we are interested in the distance between the individuals. So there are distinct individuals and we are trying to find the distance between them and how close they are or how different they are from each other. In case of partitioning methods, we are not so much interested in the individual members. We are rather more interested in the groups that are being formed. So it's the group characteristics that we would be looking at when we would be looking at the partitioning method. In the partitioning method, we separate the observations into distinct clusters or groups. We do this keeping in mind that the members within a cluster should be as similar among themselves as possible, whereas the members of different clusters should be as different as possible. In partitioning, as we mentioned before, we are focused on the cluster types and not on the individuals. So unlike hierarchical clustering, distances between individuals within clusters are not of importance, and we very seldom measure this. It is only the distinct clusters and the distance between these clusters that we are interested in. Let us look at a few examples of partitioning. First of them is how to arrange these hats on a shelf. For example, a shopkeeper who sells these hats, he has different types of hats. Now how he would arrange these hats so that a person coming to the shop looking for a particular type of hat or similar type of hats would go to a particular shelf and find what he needs. Now you can see that these hats are of different types. So there must be some criteria by which we can separate them into different shelves. That is the problem of partitioning. Another example is, look at these couples here. We have 8 couples here, so there are 16 members. Now suppose you invite them for dinner and you have 4 tables. So how to arrange these individuals at the different dinner tables? Should you have the ladies in 1 or 2 tables, the gentlemen in the other 2 tables, and then again which gentlemen to sit together, 4 of them, and which other 4 to sit at a different table? So you can have different sort of combinations depending on some criteria. And this again would be what partitioning does. The question would be then how to partition the individuals given their distinct characteristics. The 2 important questions that come readily would be, firstly, how many clusters to partition in. Mind you, if you go back to the last example I gave you, we had decided that there are 4 tables. But then we may not decide on the number of tables beforehand. We may decide on the number of tables based on the number of individuals who are similar and whom we want to have on the same table. So it might be 4 tables, it might be 3 tables, or it might be 5 tables even. So we may not be able to predetermine the number of clusters that we partition in. But then we'll come to this problem later on. For the time being, we'll assume that the number of partitions or number of clusters are known. Then how to allocate the individuals into these clusters? We will be discussing 2 different methods, the k-means clustering and the minimization of the within cluster variability. for allocating individuals to different clusters. So when we do the clusters, we begin by assuming that the n individuals are to be divided into k given clusters, and later on we'll see how this k can be chosen in an optimal manner. K-means clustering. In K-means clustering, as we said, we know the number of clusters. This is k. So we first need to define these clusters. So how do you define the clusters? We need to have a cluster center. We'll call this the k nuclei of the initial clusters. Now how do you choose this k nuclei of the initial clusters? So suppose we have n observations or members who we need to cluster. To form the initial clusters, we can choose the first k of these observations as the cluster nuclei, or we may take the every n by kth observation as a cluster nuclei. In this way we would get k different nuclei for the k clusters. In this case, n by k in the third bracket actually means that n by k can be a fraction, so take the largest integer contained in this fraction. A third method would be to select any of the k observations at random. Very often, better methods are to select the k furthest observations. So we look at the relative distance between the observations and take the k furthest observations as the nuclei of the unknown clusters. Another method is to look at the high density regions. What is meant by the high density regions is when we have a lot of members close together, we call it a high density region. And we select the clusters from among this high density regions so that they can have a large number of clusters very close to them. So any one of these 5 methods is generally used to start with. So the k nuclei are chosen, and when we look at the k-means technique, the convergence would be slightly different for each of these methods, but ultimately you would land up with the same cluster formations whichever method you start with. Therefore the initial choice is not so important. It only would be important as far as computation is involved. So some of them might take a longer time to converge, some of them might take a much less time to converge, but they would ultimately converge to the same clusters. So once having chosen the nuclei, we have k clusters defined. Now what we do is, we have n minus k remaining observations. We find the distance of the k nuclei from each of these n minus k remaining observations. Now look at any one of the n minus k observation. If it has the smallest distance from a particular nuclei among the k, then you place it in that particular cluster. So one by one we place each of these n minus k observations into its closest cluster, in the sense that it has the closest distance from its nuclei. So once we have formed the initial clusters, we next define the cluster centroids. So as before, the cluster centroids are the mean of the clusters. So xj bar is the cluster centroid of the cjth cluster. It's given by 1 by nj summation xji, where nj is the number of cluster members. Now having found this cluster centroids, what we need to look back is, we have to go back again and reallocate the observations, in the sense that having done the first set of allocation based on the single member clusters, once we have formed the centroids, it may be that one member becomes closer to another centroid than to its own centroid. Because as we have more and more members, the cluster centroids would be changing, and this member might be wrongly assigned to a different cluster. So we need to reallocate these members according to their distance from the different cluster centroids. To the nearest cluster centroid it is 2, and once we have done all this reallocation, we need to calculate the cluster centers again. So having recalculated the new cluster centroids, we again look at whether any individual is closer to another cluster center than to its own. Again do the reallocation. Recheck this until all individuals have their own centroids as the closest from itself. And now we have the final cluster by k-means technique. So we have been able to segregate the n members into k distinct clusters with k distinct nuclei. An alternative to the k-means clustering is the k-median clustering, which is not much difference except that instead of the centroids, at each step we'll be looking at the medoids, that is the median value within the cluster. And then we would be repeating the whole thing based on medoids rather than on centroids. Look at an example here. So suppose we are trying to form two clusters here using the k-means. So at step 1 here, we start by these two clusters where the blue points are in one cluster and the red points are in one cluster, and we find the cluster centroids which are slightly darker than the rest, and then we reallocate the observations which are closer to the other centroid. We keep doing this at step 2. You see the clusters changing gradually. So from step 2 to step 3, and then step 4, 5, and ultimately at step 6 we find two distinct clusters, and you can see that there are two very clear-cut cluster, one on the right hand top and the other at the left hand bottom side of the screen. Okay, so we have been able to separate this, and ultimately what happens is within the cluster all the observations are closest to its own mean. So we need not do any more reallocation, and this is the final two clusters that we have. So this is the k-means clustering technique. As opposed to this, we have what is referred to as the within cluster variability minimization technique. Now in this case, the separate clusters are formed such that the clusters are homogeneous within themselves, and the clusters are as variable as possible between themselves. Now how to do this? So for k known, in this case again we are assuming that k is known. So start as before, select k observations to form the nuclei of the k clusters and allocate the remaining n minus k observations among them according to their closeness to a nucleus. So the first step is similar to what we do in k-means clustering, but in k-means clustering we are reallocating on the basis of their nearness to the centroids. The next step here is slightly different. What we do here is we look at the variability in the data. Now the variability in the data is given by the total variability, which is T, given by summation I equal to 1 to n xi minus x bar into xi minus x bar prime. So this is a matrix, this is the total variability matrix, and gives you the variability among all the n observations. Now when you form the clusters, this total variability is actually subdivided into two things. One is the within cluster variability W, and the other is B, the between cluster variability. The within cluster variability is given by summation j equal to 1 to k, I belonging to Cj, that is the jth cluster, xji minus xj bar into xji minus xj bar prime. So if you look at the inner sum here, the inner sum actually is the within the jth cluster sum of squares. And then you take the outer sum, which is over all the clusters, you compute the total within cluster sum of squares. And then the other variability is between cluster variability, which is B, and this is the variability among the cluster centroids. So the distance between the centroids of the different clusters. Now, splitting the total variability, we find that T is equal to W plus B. This result comes out very nicely, so we can split the total variability into the within cluster variability and the between cluster variability. So it's obvious that if B increases, then W will decrease and vice versa. So what we do here is we should split in such a manner that W is small and B is large. What does these mean? The first means that W small is within cluster variability is small, that is, the cluster is homogeneous. There is not much difference between the members within the cluster. Whereas the second, B is large, means that the clusters are distinct from each other. So they are very much different from each other. So if we can split it in this way, W small and B large, then the clustering is very good. But then this would lead to homogeneous clusters which would be distinctly different from each other. But the problem is, how do you get to homogeneous clusters? If you go on increasing the number of clusters with less and less members, then obviously W would become small and B would become large. So we need to look into this more carefully. One criteria that we need to look at is minimization of trace of W. So we are trying to minimize W, therefore W is in this case of course W is a matrix, and therefore we need to look at the single scalar value which can be the trace of the matrix W. This method is simple and generally it's not variant to any orthogonal transformation. So you can make orthogonal transformations and you can still get the same W here. Minimization of the determinant of W. This is slightly difficult to calculate, but often this gives you the best result. But computationally this is slightly different. So again this leads to a single scalar value. A third is to maximize the trace of BW inverse. Mind you, in this case, unlike the previous two where we are minimizing, we maximize because we are looking at W inverse. So W minimization means W inverse maximization and also B maximization. So it takes into account both B and W inverse and maximizes the trace of BW inverse. If you look at the eigenvalues, it's obtained very simply through the eigenvalues, but if you have elongated clusters, then this is not very reliable. So it's either the trace or the determinant of the W matrix that we look at generally. In fact, using one of the alternative criteria may lead to different types of clusters. So we should be careful about this also. Next, we'll be looking at how to choose the number of clusters K. Usually K would be unknown, as we said. Okay. Now let Wk be the within cluster variability. So W was the within cluster variability, and now we have a suffix K which actually tells you that we are looking at K clusters. So suppose we decide that pre-decide that we have 3 clusters, so we look at W3. Now W3 is the final K cluster partitioning using any of the splitting criteria. So you can be using the K-means, or you can be using the minimization of within cluster variability, and once you have done the clusters, you look at the within cluster variability. Now Wk thus is the minimum of within cluster variability among all K partitions of the clusters. Wk is monotonically decreasing in K. This is something we have talked about before. That is that if we increase the number of clusters, the cluster sizes become small, there are less and less members within the clusters, and hence the within cluster variability would become smaller and smaller. So Wk would be monotonically decreasing in K. Now what we do is how to choose an optimal K. So suppose what we do is we take different choices of K and get Wk. So we are not sure as to how many clusters we should have. So we start with K equal to 2, form 2 clusters, look at Wk, then look at W3, then look at W4, taking 4 clusters. We go on doing this. And if we plot this Wk's against K, what happens is we have a declining curve. Wk would be decreasing with K. But the decline would usually be rapid in the initial stages. So as you form the first 2 to 3 to 4 stages or clusters, the decline would be in the Wk would be much larger. But once homogeneous clusters are formed, the decline in K would be much gradual as you have a larger number of clusters. Okay, so once the clusters become homogeneous, subdividing them generally does not lead to a large decline in K. So what we do is we search for what is referred to as elbow or kinks in the curve, in the plot of Wk against K. Why are we looking for elbows or kinks? Firstly, mind you, by this criteria, what would be the best number of clusters? With n observations, it is obviously going to be n. But too many clusters defeat the whole purpose of clustering. We don't really need to define n individuals into n different clusters. We need to put them together, group them together, so as small clusters as possible. Okay, so too many clusters would defeat our purpose. And then beyond the elbow, increasing the number of clusters does not much improve the within cluster variability. So we should stop when we find that we have very distinct clusters, and then splitting them does not lead to any better result. So if you look at this diagram here, this is a plot of Wk against K, and you can see that at around 3 or 4 the decline becomes gradual. So you can decide on K being equal to 3 or 4 in this case. An alternative method of choosing K is the Kalinske and Harbaz method. In this case, what they look at is a statistic which is referred to as Ck. This is the ratio of the trace of B and W into the ratio of the degrees of freedom, that is n minus k and k minus 1. And if you plot Ck against K, what you'd find is that Ck initially rises and then falls. Now, optimal K is obtained at the peak of this rise and fall. So initially it would be sort of a quadratic curve which would be maximizing at some point, and the peak that you get would correspond to the best or optimal K. Why is this? Because the trace of B would be increasing as you increase the number of clusters, and the trace of W would be decreasing with the number of clusters. Whereas if you look at K, if you increase K, then n minus k would be decreasing and k minus 1 would be increasing. So this second factor would be actually decreasing with k. So the first factor increases with k and the second factor decreases with k. So there is a trade-off. So once you go beyond the optimal number of clusters, then this ck value would start falling, and you should stop when you reach the peak. In some cases, you might have a monotonically increasing value of ck, which would imply that you don't have any clusters. So you need not form any clusters. You put them all together. If they are all monotonically decreasing, then you use a hierarchical clustering methods and put all the individuals. The best thing that you can do is put them all in n different clusters. That is the bottom of the tree. So if they are monotonically increasing, you don't do a clustering. If ck is monotonically decreasing, then you do a hierarchical clustering. So this is how you can do partitioning, and this is how you can choose the k number of clusters that you partition the observations in. In today's module, we have discussed the partitioning method of clustering. Recall that there are two distinct questions that we need to address when we are looking at partitioning method. The first of them is the choice of the number of clusters. Very often these are not very well defined. So a group of objects may be divided into 3 clusters, 4 clusters, or maybe 5 or 6 clusters. So how to decide on this? The second is how to partition the members into these distinct clusters. We have discussed two methods, which are the k-means clustering. An obvious corollary of the k-means clustering is the median clustering. The alternative method is to look at the within cluster sum of squares and partitioning clusters such that this is minimized. Finally, what we have looked at is how actually we select the number of clusters based on the within cluster sum of squares, the information contained in that, and some of the measures based on the within cluster sum of squares, which helps us to define the number of clusters which would be optimal for a given set of observations.